What are we learning today? There's a lot of interesting stuff on the table.
Today, we will learn about sound.
Yay!
Joy doesn't have to learn about it.
Why do you say that, Devi?
He's always making a lot of funny sounds.
Peow!
See? I told you.
That's noise, Joy. Keep quiet.
You heard that, Joy? That's noise. Disgusting noise.
Okay, that's enough. Now both of you keep quiet and think about this. What do we have to do to produce sound? In other words, when is sound produced?
When we strike something, like hitting the table with our hand or striking a steel plate with a spoon.
What happens to the body when it is struck?
It vibrates.
That's right.
It vibrates? You mean it moves to and fro? Or back and forth? I can't see it vibrating. Then how do we know it's vibrating?
That's a good question. We can't see it vibrating because it vibrates very fast. We can do a small experiment to show the vibration.
Really? I want to see it. Wow, that's beautiful.
Can we do another experiment?
Surely, why not? Watch this. Here is a tuning fork that is not vibrating. I touch the polystyrene ball with this tuning fork. What do you notice? Nothing happens. This time, I bring the tuning fork after striking it against the table. Now, I touch the polystyrene ball again with this tuning fork, and what do you notice? The ball has gone flying off. This can only happen when the tuning fork is vibrating.
This is fun!
Now are you convinced that the tuning fork was vibrating when it was struck? We have a violin here. Let's put that to good use. When I pluck the string, you can hear a sound. But can you see the vibration of the string?
No, we can't.
So, what I'm going to do is place a small piece of paper on one of the strings and pluck that string. See what happens? The paper jumps off the string. This can only happen if the string is vibrating. We can't see the vibrations because they are so fast.
How fast?
Good question. Y'all are asking just the right questions. I'm so impressed with y'all. To answer your question, Devi, of the sounds we can hear, the slowest vibration is 20 times per second, and the highest we can hear is 20,000 times per second.
Ooh, that's huge.
Since y'all have brought up the question, here's a little definition. The number of vibrations per second is called the frequency of the vibrating body. And one vibration per second is said to have a frequency of 1 Hertz. So, a human hearing range is from 20 Hertz to 20,000 Hertz. To wind up today's lesson, I'll leave you with 2 questions to think about. 1. How does the sound travel from the vibrating body to our ears? And 2. What really travels when sound travels? Well, that's all for today. See you again in the next lesson on sound. Bye-bye. Hello and welcome to our second lesson on sound. At the end of the last class, I had asked 2 questions. Do you remember the questions? And have you found answers to them? But where is Joy? Why don't I see him today?
He's gone for singing practice.
Okay. Now coming back, the first question I had asked was, how does sound travel from the vibrating body to our ears? Do you have the answer to that?
Yes, I read it up. Sound travels as waves.
What kind of waves?
Longitudinal waves. Funny name.
It's not funny.
Yes, funny.
Not funny.
Yes, funny.
Okay, it's funny. Now look this side.
What is a longitudinal wave?
Good question, Devi. Let me show you a picture first, and then an animation. Look at this picture. This is a snapshot of a longitudinal wave. What you see in this are regions of compression and regions of rarefaction.
I can only see a lot of dots.
That's right. Imagine each of those dots to be molecules of air. So, as sound travels through air, the molecules alternately get compressed into high pressure zones and rarefied into low pressure zones. These compressions and rarefactions travel through air from the source of the sound. You will understand better when you see the animation. Here's an animation of a single pulse of sound traveling through air. You can see the region of compression moving forward, and immediately behind it, a region of rarefaction.
Ah, now I understand. This is what happens when a single sharp, short sound travels through air?
Yes, a sharp, short sound is a pulse.
If Joy was here, he would have produced a pulse just now.
Ha! You are funny.
But if a series of pulses were produced, then we would have compressions like that following each other with rarefactions in between.
Yes, that's right. Now does this picture make more sense to you?
Yes, I'm liking this. But you had another question as well. What really travels when sound travels?
Yes, I did. So what is the answer?
I don't have a clue.
Ah, the simplicity of the answer will surprise you.
Really? Can I make a try? And make a mistake?
Oh, of course you can. Tell me.
I think it's energy.
That's absolutely correct. It is energy. Is that a guess? Or have you been reading about it?
I have been thinking about it. I remember being taught that energy cannot be destroyed or created. It can be transferred from one body to another. So, it must be the energy that is being transferred.
Devi, that is brilliant. You are doing so well. You're absolutely correct. It is energy that is transferred when sound travels.
I'm so happy. Understanding my studies makes me very happy. That's such a beautiful thought. Understanding your studies makes you happy. Did you hear that, students? That is something all of you must remember. In the next class, we will look at transverse waves and then some more definitions. Bye-bye then. Devi, say bye-bye. She's lost. She's lost in her own world. Devi. Bye-bye. Science is fun, I tell you.
Hello and welcome to our third lesson on sound. How are you all doing, Devi and Joy?
I'm happy. I'm excited.
That's so good to hear. At the end of the last class, I had mentioned that in the next class we will look at transverse waves and then some more definitions. Let's start. To recapitulate quickly, longitudinal waves are those waves in which the particles of the medium vibrate back and forth along the direction of progress of the wave. Now, let us move to transverse waves. Here's a graphical representation of a transverse wave. This is the kind of wave you see on the surface of water or the wave formed by a fluttering flag. As you can see, in this type of wave, the motion of the particles of the medium is perpendicular to the direction of propagation of the wave. It's like a T, capital T. So it should be easy to remember. Now, let us have a look at some of the basic definitions with respect to a wave. In this visual, you can see both the types of waves. Let me mark for you the distance that is called wavelength of a wave. As you can see, the wavelength is simply the length of a wave. It is the distance from crest to crest, or from trough to trough of a transverse wave. So, wavelength is the distance between successive crests or successive troughs of a transverse wave. Now, coming to a longitudinal wave, wavelength is the distance between the midpoint of a compression to the midpoint of the next compression, or wavelength is the distance between midpoint of a rarefaction to the midpoint of the next rarefaction. So, wavelength in the case of a longitudinal wave is the distance between the midpoints of two successive compressions or the distance between the midpoints of two successive rarefactions. That is simple, isn't it? That's the length of a wave. All you need to remember is from where to where is the length of a wave. Clear?
Yes, that is simple. But you had mentioned amplitude in one of the pictures. What is amplitude?
Good question, Joy. I was waiting for one of you to ask this question. Amplitude is the maximum displacement of the particles of the medium from the mean position. In this figure, you can see the amplitude marked. In this figure, you can see that the red wave has a higher amplitude than the green wave. So, greater the maximum displacement, greater is the amplitude.
Okay, I get that. That is pretty straightforward. Is there any other definition for today?
Just two more definitions. Look at this picture. In both the diagrams, the x-axis measures time. Now, If you count the number of complete waves in the upper diagram, you will see there are 14 of them completed in 10.5 seconds. Whereas in the lower diagram, there are 10 waves completed in the same time of 10.5 seconds. So, here's the new idea. How many waves are completed per second? Then, in the upper diagram, the number of waves completed per second is 14 waves divided by 10.5 seconds, that is 1.33 waves per second. And in the lower diagram, the number of waves completed per second is 10 divided by 10.5, that is 0.95 waves per second. So, here's the definition. The number of waves completed per second is said to be the frequency of the wave, and it is measured in hertz. So, the upper wave has a frequency of 1.33 hertz, and the lower one has a frequency of 0.95 hertz. Here's the definition of a hertz. If one wave is completed in 1 second, then the frequency of the wave is said to be 1 hertz. And here is the last definition for today. The time taken to complete one wave is the time period of the wave. Thus, the upper wave has a time period of 0.75 seconds, and the lower wave has a time period of 1.05 seconds. Hope you all have understood the definitions. As the lesson progresses, we will be using these terms very often, and so you must become familiar with their meaning and definition.
Thank you, sir.
Thank you, children. Hello and welcome to our 4th lesson on sound. I hope all of you are doing fine.
Yes, thank you.
Yes, I'm fine too. Thank you.
In the last lesson, we learnt the definition of frequency. Who can tell me the definition of frequency?
I can.
I can.
Okay, Devi, tell me.
Frequency is the number of waves completed per second.
And what is the SI unit of frequency, Joy?
It is hertz. If one wave is completed in 1 second, then the frequency of vibration is 1 hertz.
That's good, Devi and Joy. Well, today we want to learn what aspect of the sound we hear changes when frequency changes and what changes when amplitude changes. So let's look at frequency first. Look at this picture. The upper waveform has a higher frequency than the lower one. This is because the upper one completes a greater number of waves in 9 seconds than the lower one. In fact, the upper one completes 12 waves while the lower one completes 5 waves, both in a time of 9 seconds. So, the upper wave has a higher frequency than the lower one. The upper one has a frequency of 1.33 hertz, while the lower one has a frequency of 0.56 hertz. But these are waves that I have drawn to explain the idea of frequency. Let us now look at the wave patterns of some pure notes in the human audible range.
Really? Do they look different?
No. Here you are. Look at this. This is a pure note. Pure notes have a single frequency in them. This one has a frequency of 220 hertz. the x-axis shows time in seconds, and between the two yellow-orange lines, the time axis reads 0 to 0.050 seconds, and the y-axis shows amplitude. Let us listen to the pure note of frequency 220 Hz. The highlighted portion shows one wave. We can calculate the frequency from the wave pattern also. There are 11 waves, as I said, completed in 0.050 seconds. Thus, its frequency is 11 divided by 0.050, which is 220 Hz. Before we go on to the next pure note, let us listen to 220 Hz again, so that you can understand the difference in the notes. Let us play this note now. This is 440 Hz. Children, do you notice the difference?
Yes, this is shriller.
Yes, this has a higher pitch.
Can we see how their waveforms compare?
Surely. Here you are. There are 22 waves completed in the same 0.50 seconds. So the frequency will also be exactly double. Let us play the two notes one after another again. Now, let us listen to two other notes, 800 Hz and 1600 Hz. In the upper waveform, there are 40 waves completed in 0.050 seconds, which means it has a frequency of 800 Hz, and the lower waveform has 80 waves completed in the same 0.05 seconds, which means it has a frequency of 1600 Hz. By now, you surely must have understood which quality of the sound we hear changes when frequency changes. Now, let us look at amplitude. Here, you can see two waveforms. Both have the same frequency of 220 Hz, as both complete 11 waves in 0.05 seconds. But the upper waveform has a smaller amplitude in comparison to that of the lower one. So, the question is, what aspect of a sound changes when we change its amplitude? Let us play the two pure notes. First, the upper one with the smaller amplitude. Now, let us listen to the waveform with the larger amplitude. So, what difference did you notice between the two sounds?
The second one was louder.
Yes, the second sound was louder than the first.
Now you understand the difference that amplitude makes to a sound? When you increase the volume of your TV or radio or mobile phone, you are actually increasing the amplitude of the sound. That is all we had set out to learn in this lesson. But before we wind up, a quick recap. As we increase the frequency of a wave, its dash increases.
Pitch increases.
Pitch increases.
That's right. And as we increase the amplitude of a wave, its dash increases.
Its loudness increases.
That's right. So I'll see you all again in the next lesson. Bye-bye.
Bye-bye,
Bye-bye, sir.